Del segundo día de nuestro Seminario de Medicina de Precisión, y en esta ocasión tenemos la plática del doctor Sinue Barroso Bravo. Él pertenece al Hospital de Oncología del Centro Médico Nacional Siglo XXI. Muchas gracias, doctor, por aceptar esta plática y bienvenido.
Buenos días, agradezco mucho la invitación. La UMA Hospital de Oncología se siente honrado de estar participando en estas pláticas tan importantes y además se siente honrado de estar en esta casa de la cultura y muy importante para la vida científica y cultural de México. El título de la charla es El papel de la UMAE, Unidad Médica de Alta Especialidad, Hospital de Oncología, en la prestación de servicios de pacientes con cáncer en el Instituto Mexicano del Seguro Social. Este es el plan de presentación, quiénes somos, nuestra cartera de servicios, factores diferenciadores de éxito, docencia, investigación, certificación médica, inclusión y diversidad. La misión de la UMA Hospital de Oncología es otorgar la atención médica integral de calidad a pacientes con cáncer y desarrollar educación e investigación que permitan satisfacer las necesidades y expectativas de los usuarios y prestadores de servicios acorde a principios éticos con administración transparente de recursos institucionales. Y nuestra visión es ser el mejor hospital de prestación de servicios médicos en oncología de nuestro país, en las áreas de prevención, diagnóstico, tratamiento y rehabilitación de pacientes con cáncer, otorgando los mejores productos y servicios médicos con un enfoque humanístico centrado en el paciente y fomentando un modelo competitivo de gestión de calidad total. Vamos a ir desarrollando precisamente esta misión y visión de la UMA Hospital de Oncología. La Unidad Médica de Alta Especialidad del Hospital de Oncología es un hospital único en su tipo en el Instituto Mexicano del Seguro Social, el único que se dedica exclusivamente al diagnóstico, tratamiento y rehabilitación del cáncer. Como en el Instituto Mexicano del Seguro Social hay una regionalización, nosotros tenemos acuerdos de gestión con estas entidades federativas que se relacionan con los derechohabientes del IMSS en los estados de Chiapas, Guerrero, Hidalgo, Morelos, Querétaro, la Ciudad de México en las delegaciones norte y sur y las delegaciones del Estado de México Oriente y México Estado Poniente. Esto potencialmente corresponden a 16 millones de derechohabientes que los que tengan diagnóstico de cáncer potencialmente pueden ser atendidos en la UMA Hospital de Oncología. Y estamos ubicados en el Centro Médico Nacional, en la colonia de Doctores en Cuauhtémoc 330, a sus órdenes para servirles. Esto es simplemente para que ustedes vean que la mencionada transición demográfica alcanzó a la UMA Hospital de Oncología. Si ustedes ven, a partir del año 2005, incrementamos el número de atención de pacientes de primera vez y que tiene que ver también con la atención de pacientes subsecuentes en un 51%. Esta significa que nuestra carga asistencial prácticamente se incrementó en la mitad en una década y estamos con una infraestructura prácticamente igual. De manera entonces que tuvimos que hacer y modificar nuestro modelo de atención con la finalidad de poder brindar una atención adecuada a nuestros pacientes. El Instituto Mexicano del Seguro Social brinda atención regionalizada. Sin embargo, cuando hablamos del papel de la UMA Hospital de Oncología en el Instituto Mexicano del Seguro Social, ustedes observen cómo hasta un 17% de los pacientes que acuden al Hospital de Oncología son de una región distinta a la regionalización. Significa entonces que nosotros vemos pacientes de todo el país, significa que no les decimos que no a los pacientes que vienen de otro sitio. Significa que la UMAE Hospital de Oncología tiene la significancia de poder tratar pacientes especiales que no pueden ser tratados en otros sitios en el Instituto Mexicano del Seguro Social. ¿Cuál es nuestra cartera de servicios? En un día típico otorgamos en promedio 739 consultas subsecuentes y 45 consultas de primera vez. Déjenme comentarles que este número de 739 consultas más las 45, quizá tengamos un problema de registro. La carga asistencial a veces es tan ardua que no alcanzamos a registrar el número completo de pacientes que vemos, porque si revisamos el archivo clínico, encontramos a veces que sacamos hasta 900 a 1100 expedientes diariamente. Hacemos de 75 a 80 valoraciones en admisión continua, 40 ingresos hospitalarios, de 26 a 30 intervenciones quirúrgicas por día, 830 estudios de anatomía patológica, 86 procedimientos de medicina nuclear, 203 estudios de imagenología, de 17 a 18 resonancias magnéticas, 83 tomografías computadas y 3.611 pruebas de laboratorio. Esto es simplemente para reflejar la carga asistencial de la UMAE Hospital de Oncología. Y la infraestructura que tenemos es que tenemos un servicio de admisión continua, urgencias, de hospitalización que tiene 144 camas sensables, tenemos un área de aplicación de quimioterapia con 26 sillones para aplicación de quimioterapia, se aplican más de 120 quimioterapias ambulatorias por día, una unidad de cuidados intensivos, un área de imagenología con equipos de radiología, ultrasonido, mastógrafos, resonancia magnética, en el área de medicina nuclear 2 gamacámaras y quizá el área donde haya mayor tecnología en la UMAE Hospital de Oncología es en el área de radioterapia. Recientemente se adquirieron 4 aceleradores lineales y hoy día, en este año, estamos adquiriendo 2 aceleradores lineales más, además de un equipo de CyberKnife, que es un acelerador lineal de cirugía robótica, que es único en el país, y proporcionamos a través de los departamentos de cirugía, de medicina, de radiooncología, estas especialidades de oncología médica, hematología, medicina interna, y la parte quirúrgica la dividimos en servicios de cabeza y cuello, colon y recto, ginecología oncológico. Esto es para dar una atención más personalizada y a través de especializar a los cirujanos, a los oncólogos médicos, a los hematólogos, a los radiooncólogos, con la finalidad de que este expertise favorezca el resultado de los tratamientos. ¿Qué factores nos hacen diferenciadores de éxito? Bueno, pues hay un liderazgo participativo de la UMAE Hospital de Oncología que no solo trasciende al Instituto Mexicano del Seguro Social, sino a todo el área de la salud. Construimos y actualizamos las guías de práctica clínica en oncología. El 90% de estas guías de práctica clínica se realizan en el Instituto Mexicano del Seguro Social y la UMAE Hospital de Oncología, su personal, es el líder en la creación y construcción de estas guías de práctica clínica. Aplicamos esas guías de práctica clínica a través de grupos interdisciplinarios e implementamos modelos de atención por grupos específicos, esto es, a través de lo que se conocen como comités de tumores, que es una atención interdisciplinaria, y estamos evolucionando a la creación de unidades funcionales. Una unidad funcional, a diferencia de la atención que está como partida, un paciente que llega, se le hace el diagnóstico, pasa con el cirujano dice yo lo opero, después de cirugía lo manda a oncología médica y de oncología médica a radioterapia. Entonces es una atención muy lineal y en la actualidad esta atención se debe de dar de manera interdisciplinaria, de manera que entonces el objetivo es que en un solo sitio esté todo el equipo de imagen, equipo de endoscopia, equipo de oncólogos médicos, cirujanos, internistas, y que al mismo tiempo estén evaluando un paciente, lo cual evita que existan estas citas y la atención sea más personalizada e interdisciplinaria y con una toma mejor de decisiones. Somos un hospital certificado por el Consejo de Salubridad dentro de lo que corresponde a las unidades médicas de alta especialidad en el Instituto Mexicano del Seguro Social. Son 3 hospitales que están certificados y nosotros somos uno de ellos. Al final, nosotros queremos tener un modelo de atención asistencial, vean ustedes la carga asistencial que tenemos, pero combinado con una docencia de investigación, con un enfoque en la gestión y calidad y seguridad del paciente. Esto es ver cómo esta carga asistencial a través de un modelo de gestión de calidad y con un enfoque en la investigación nos puede dar un factor diferenciador de éxito en este país. Un ejemplo de liderazgo: sabemos muy bien que un problema muy importante del país son los cuidados paliativos a pacientes terminales. En el año 2012 se hizo la norma oficial mexicana donde se pusieron los criterios para la atención a enfermos en situación terminal y un acuerdo por el que el Consejo de Salubridad General declara la obligatoriedad de los esquemas de manejo integral de cuidados paliativos. Esto es algo que la UMA Hospital de Oncología es el líder a nivel nacional y no solamente en la institución, sino también en la Secretaría de Salud para la implementación y para cumplir con estas normas tan importantes. Y respecto de la carga asistencial, el gran número de pacientes que nosotros vemos, ustedes vieron cómo se incrementó el 50% de nuestra carga asistencial en los últimos 10 años. Esta es una encuesta de Verumen que se hizo en el mes de abril y vean cómo la satisfacción que muestra nuestro derechohabiente de la atención del personal de la UMA Hospital de Oncología es del 94%, arriba del promedio nacional. En docencia, generamos especialistas en las áreas de cirugía oncológica, de ginecología oncológica y de oncología médica. Y ustedes pueden ver aquí, está por años, porque esto corresponde a los 4 años que deben de pasar los médicos residentes para obtener esta especialidad, y vemos que hay 38 médicos residentes del área de cirugía oncológica, 14 del área de ginecología oncológica, 27 del área de oncología médica, para darnos un total de 79. Todos estos especialistas van a estar en el Instituto Mexicano del Seguro Social y también están en la Secretaría de Salud. Es decir, la UMA Hospital de Oncología es formadora de recursos de alta calidad, medicina del trabajo, son al final 19, y radiooncólogos 42, para darnos un total de 61. También es formador de personal técnico, técnicos en medicina nuclear. Estos son 2 años para ser técnicos en esta área, y en este momento estamos formando 24 técnicos en medicina nuclear y técnicos en radioterapia. ¿Sí me podrán ayudar o no? Ese es. 17. El número de publicaciones generadas en la UMA Hospital de Oncología se ha ido incrementando del año 2015 al año 2007, y el impacto que tienen estas publicaciones también. Los investigadores dedicados al área clínica y al área de investigación básica 14 tienen doctorado y 8 tienen maestría. Aquí es muy importante comentarles que a partir de este año, la UMA Hospital de Oncología tiene un convenio con el Instituto Politécnico Nacional para que sea la sede de la maestría en investigación clínica. Incluso si hay alguno de ustedes por aquí que quiera participar y hacer la maestría en investigación clínica, se puede acercar con nosotros porque esta maestría va a iniciar. Se está tratando de hacer un modelo en el hospital donde el médico residente que llega forzosamente tenga que tomar un seminario de investigación que puede ser en línea, que puede ser presencial, y quien quiera hacer la maestría en investigación la puede hacer. Y también para los médicos adscritos, enfermeras, hacer la maestría en investigación y establecer líneas de investigación para que cada uno de los pacientes que esté en proceso de atención en nuestro hospital esté en una línea de investigación. Es crear un modelo donde el lenguaje sea la investigación. Sobre la certificación médica, el 99% de nuestros médicos están certificados por el Consejo de su especialidad. Los que no están certificados aquí, que son 2, estamos en proceso de que lo hagan, dado que es un asunto de ley. Nosotros entonces estamos trabajando para cumplir con ese 100%. Y respecto de inclusión y diversidad, el Hospital de Oncología tiene 1,729 trabajadores en este momento activos. El 44% son hombres y el 56% son mujeres. Aquí también cabe aclarar que en un hospital el porcentaje de mujeres se incrementa porque son un buen número de enfermeras, estamos hablando de 600 enfermeras. De modo entonces que respecto de la diversidad, no podríamos decir aquí que sea porque haya una relación de favorecer la equidad de género. En el caso de los médicos no familiares especialistas, estamos, digamos que, casi a la mitad, todavía hay más médicos hombres que mujeres. Sin embargo, en lo que corresponde a la alta dirección, y estamos hablando de divisionarios, directores de área, el 58% son mujeres. Entonces, vean ustedes esta tendencia que se está haciendo nacional, está ocurriendo en la medicina y nosotros estamos muy contentos de que esto ocurra así. Muchas gracias.
Muchas gracias, doctor Barroso, por dar este panorama de lo que está sucediendo en la Hospital de Oncología en el Centro Médico Nacional. Y llegamos ahora a la presentación, a la última presentación de este seminario que dará el doctor Yamaguchi, Rui Yamaguchi. Él es parte del Centro del Genoma Humano del Instituto de Ciencias Médicas de la Universidad de Tokio y nos hablará del desarrollo de herramientas para el análisis de datos para la inmunofarmacogenómica. Bienvenido, doctor.
Thank you very much for the introduction. So, I'm very happy to be here, and it's very my great honor to be here and to present our study. And first of all, I would like to thank the organizers, especially for the Professor Espinosa and Professor Martínez. Today, I would like to talk about the development of mostly the data analysis tools for immunopharmacogenomics. That is a long term, is a joint word, is immunology and pharmacogenomics. That is actually originally coined by Professor Nakamura. So as you understand the importance of the immunology and the genomics you heard the previous talks. As you heard the previous talks. So okay, due to the developments of the drastic developments of the measurement technology in biology, so nowadays we can now observe the multimodal data in unprecedented ways. So here is an interesting example study. So in this study, a single healthy person from the single healthy person man, he took the multimodal data, genome data, and transcriptome data, and the metabolite data, and the immune cytokine data, and so on, more than nearly 2 years. So during the time course, so this person got infectious disease twice. The first time is HLV, human line virus, is for the cause of the common cold, and the second time is he took infected by the RS virus, and here is the cytokine heat map of the several cytokines, and here is the time course. The horizontal axis is the time course, and during the infection, he got the cytokine pattern is drastically changes. So from this study, so we can get ideas. So by observing or monitoring the immune systems, we can prevent, or we can consider the new therapeutic ways, including the cancer therapy, immunotherapy, like that. So we have been developing various computational methods to generate immunogenic profiles from NGS data, not only the NGS data, and for example, the T cell and B cell repertoire analysis. So that is presented in the morning by Dr. Kiyotani, and also we have developed the HL genotyping from the low depth data from WGS. That is also presented by Dr. Imoto, and also we have developed some pipelines for neoantigen detection or the predictions. That includes mutation calling from the low variant allele frequency mutations, and also the neoantigen prediction pipelines. So due to the time is limited, so today I would like to talk about the T cell, B cell receptor analysis pipeline that developed in collaboration with Professor Nakamura's group. And the T cells, as you know, are involved in the adaptive immune system. So that recognize the peptide antigen bound to MHC. So in human, the HLA expressed on the surface of antigen presenting cell that is called APC, and T cell receptor is important for recognition of the antigen, as Dr. Kiyotani presented today. And the antigen presenting cell APC show the antigen on the HLA, and each specific antigen recognized by each specific T cells. Like that. That is a relationship with the key and the keyhole. So we call the T cells which have the specific TCRs, it's called clones. So there are several types of clones. So by monitoring the dynamics or behaviors of the changes of the T cell repertoire to the clones, that is called also repertoire, is important for understanding the mechanism of the immune systems. And the T cell receptor is a dimer of the alpha chains and the beta chains. Heterodimer. And using the T cells that recognize antigens and here. And the T cells is very diverse because that can get such diversity from the genomic rearrangement after the birth, the somatic rearrangement. So the mechanism of the getting the rearrangement is here. For the T cell alpha, that is consists of the B segment and the J segment. So that gets randomly choose one of the V segment, V gene, and one of the J gene. And also the T cell beta chain is much more complex. So one of the beta is selected, and one of the D gene segments is selected, and one of the J is also selected. And after the one of the C, constant region is selected. That is not the genomic rearrangement. The C is not due to the genomic rearrangement. But the combination is makes the huge diversity. So in more details, so not only the combination of the one of the V or the J genes, so it usually includes the deletions between the other junction part of the V and the J. There is a deletion, and also it becomes the non-templated sequence that is not coded in your human genome is randomly inserted. So that is, we get the V and J and C segments in the transcripts of the alpha chain. And for the beta, also the one of the B and this part is deleted, and also here is the deleted, and the J is deleted, and the non-templated part is N1 called N1, and then 2 is inserted randomly. So that randomness makes a huge diversity. The possible number of the combinations becomes 15 more than 15 times 15 powers of the 10. So if we can observe or dissect such complex diverse T cell clones from the sequence data, that is, we can obtain one of the new technology to observe the observe the biological systems, immune systems. So, in collaboration with Professor Yusuke Nakamura's lab since 2013, we started to develop the software pipeline called TCLIP, that is the abbreviation of TCR immunoprofilers. So that pipeline consists of the two parts. The one is a regular analysis part from the sequence lead that dissects into the lead sequence into the B, D, J segments, and by mapping the leads into the different sequences. And after that, I will explain later the CDL complementary determination region 3 sequence. That is important part of the anti-recognition is determined, and then gathering these chronotypes, the count of the same types of the chronotypes, and they estimate the TCR repertoire like that. And the second part is a unique part of our pipeline, is unmapped part analysis. So that is the part is for identifying new exon candidates that is not recorded in a reference sequence database. Okay, from the since 2013, the February, I and Professor Miyano visited the Professor Nakamura's lab in Chicago, and then Professor Nakamura kindly explained the details of this project and asked to develop new tools to dissect these TCR repertoire. And Professor Miyano answered immediately, so no problem, so let's go ahead. So actually, there are, after that, there are so many problems we have to solve. But we did so many hard work. So actually, we did every 2 weeks, we did the Skype meeting, and the counterpart is Dr. Gyotani, and with experiment and optimize the experiment conditions. And our side, we tuned or developed a new algorithm to make this whole pipeline. And that was, so from this experience, I learned to make good tools for biology or medicine. The tight collaboration with the biologist and biomatician is very important. And this is a workflow of the TCR sequences that from the RNA sequence data of the alpha chains or beta chains with sequence by using the PGM, ion PGM, and currently we mostly use the MySeq sequence data. And we obtain the first Q sequence data, and data analysis would be done by TCLIP pipeline. And after the sequence of the transcript, so in the transcript we have the B, N1, D, N2, J, C segments. But after the sequence, we obtained these great sequence, ATGC sequences, but we cannot identify, we cannot know, we don't know the boundary and the types of the B segments and J segments. The goal is to analyze these sequences to identify the junctions and which genes, type of the genes are included, which type of the N1 non-random sequences are included in this gray sequence lead. So I'll show you how to do that, how to identify that. So we mapped the lead sequence onto the different sequence, so one by one, and then identify the C part and J part and the B part. And after identification, the B and the J part, so these segments are between the B and the J segments. So that must be included. It must include the D segment, part of the D segment, and the new N1 and N2 segment. That is a whole process, basically whole process of the so determinations of the segments or clone typing of the this lead. So after the sequencing, the determination of the BD segments, we identify the amino acid sequences here. That is called the CDR sequence, CDR lead sequence. So in more mathematical way, we consider these functions. That here the lead sequence and map to identify the most similar B genes and to identify the coordinates on the leads and the different sequence. This is the output of the example of the T-clip. So this is the usage distribution of the usage of the B segments and D segments, J segments. We can see the here the most of the sequences, the most abundant B gene in all of the clones. I can read that maybe B7-4, and this is a distribution of the clone types that is characterized by the unique B, N1, D, and 2 J segments. And this is a log scale and actually the very long tail distributions. And after the clone typing, after obtaining the unique sequences, we estimate the CDR amino acid sequence, the starting from the second conserved cysteine in the B segment, and this ended at the coded in the J segment, the phenylalanine in the J segment, and this is the and here is the counts of the clones and the fraction here, and you can see the distributions of the clones, and we can summarize these distributions into the diversity index. So diversity index is a notion often used in the ecology that represents an effective number of the types of the species in the environment. In that case, the types of clones. And here is two cases, and highly diverse and almost less diverse, almost monoclonal. So if the abundance of each clone is similar, in that case, the diversity, we call the diversity, these clones are diverse. But if the most abundant the sequences, the dominant, one of the a few number of the clones is dominant. In that case, we say the less diverse or monoclonal. Then we can summarize the numbers like that and like that. Okay, this is the whole process of the T-clip software, and I would like to show you some example that's mostly done by Professor Nakamura's lab. And this is a result of the clone typing from the colorectal cancer patient after the administration, before and after the administration of the vaccine treatment, cancer vaccine treatment. And this is the clone types, unique clone types. And this is different samples. These samples are taken from the peripheral blood, and these samples are taken from the cancer specimens. And you can see the different clones appeared after the before and after administration of the cancer vaccine. But interestingly, in the peripheral blood, the structure of the clone or distribution of the clones are more stable than the tumor part. So we may obtain the dynamics of the cancer vaccine like here, from here. And this is another example of the changes of T-cell repertoire by nivolumab treatment. So you can see the several T-cell clones were clonally expanded in tumor responders. Here, the clonal expansion means the diversity is reduced. So in the responder, the diversity is smaller than the non-responders. This is another example is the breast cancer treated with the adjuvant chemotherapy. So you can see that in the complete response responders, the diversity is changed after the reduced after the neoadjuvant chemotherapy. That is some clonal expansions observed in the complete responders. But interestingly, the partial responders or non-responders doesn't show such significant changes. And here's another example, and the T-cell repertoire and the neoantigen analysis of bladder cancers. So you can see the several T-cell clones which can recognize neoantigens or oligoclonal antigen non-recurrent tumors. This is the non-recurrent samples and the recurrent samples. So you can see the non-recurrent part in the diversity is very small, and that means the oligoclone, so the clonality is very small. So you can maybe that represents the tumor microenvironment, and that's associated with the prognosis of the or recurrence of the tumor bladder cancers. Okay, this is another example for the not cancer treatment. This is hematopoietic stem cell transplantations patient, and after the transplantations, there are some patients produce severe side effect called GVHD, that is graft versus host diseases. So they compare the diversity of the T-cell clones of the non-GVHD patients and the GVHD patients. So interestingly, so GVHD patients, you can see the low diversity. So that is a very monoclonal, small number of clones, small types of the T-cell clones may attack the host cells, like this one. So in the GVHD part, so donor T cells attack the monoclonal T cells attack the donor cells, the host cells. And the non-GVHD case, there are diverse clones, but that don't attack the host cells, and that situation represented by these T-cell diversity, difference in T-cell diversity. That. And another example, interesting example, that is not that is for the Crohn's diseases, and so they sequence the Crohn's disease samples and they identified shared the common clone types in the different patients. That means maybe they recognize the same target, these T cells, the same target. So that may give us the clues to understand the mechanism of the clone diseases. Okay, and here is the mapped part analysis. We can also identify, we could identify the new exon candidates in the TCR beta, B genes, like that. That is identified in an unmapped part. Unmapped means that could not be mapped to the known difference sequence in the B genes. So we gathered, so our tools gathered these sequences automatically and classified, and then after that we see the more detail to identify the new exon sequences. The details of these pipelines included in this book wrote with Professor Nakamura's group. So I'm happy here our names here. And finally, I will show you briefly the BCR immune profiler. The most of the part is similar to the TCR repertoire analysis, but we should consider the isotype of the heavy chains of the BCR receptor, the IgA, IgD, IgG, E, M. So our pipeline can automatically estimate, detect the isotypes of the sequences. So getting the mechanism to getting the diversity is the same or similar to the T cell receptors in the BCR cases. So we can see the correct IgA isotype could be detected by our tools. And also, this is the samples from the oral immune therapy treatment for the peanut allergy, and the BCR repertoire is analyzed by using our tools. And we can see the oral immunotherapy sample. We can see that after the before and after the administration of the therapy, we can see the changes of clonal expansion in the IgA, IgHA, heavy chain A, and the IgHG samples. But in the placebo, we cannot see such kind of clonal expansions. And also, we could identify the candidates of the candidates of the new exons that is consist of the mixed with the IgHB, C-7, and C-21. And another example of the BCR repertoire analysis for the Kawasaki disease, that is a kind of the autoimmune disease. And after the intravenous immunological globulin IVIG therapy, so after the IVIG therapy, so some and the sensitive patient and the non-sensitive patient, resistant patients. So we can see the difference of the clonality in the IgM samples. So in summary, we have developed various computational tools or methods to generate immunogenic profiles from the next generation NGS data. And today I explained the T-cell B-cell receptor repertoire analysis pipeline. And these methods would become, I hope, inevitable tools for precision medicine. And also, we learned a tight collaboration with biologists and bioinformaticians are crucial for making the efficient tools and also to derive the useful information from the data. Okay, since 2013, we started a bi-weekly Skype meeting, and after that, several years later, Professor Espinosa, the Martha, joined our team, and that is hotlines we made. And after this meeting, we get much more sick pipelines, and we got the bond. So anyway, so and also I'll tell you that we made many tools, and some of them our students will talk in a workshop. The second day of the workshop, the Hiroki Konishi talked about the B-cell receptor sequence classification via deep learning method. And Shuto Hayashi will present HA genotyping from whole genome sequence data by Bayesian modeling. And the Takuya Moriyama present a kind of the new low variant frequency mutation coding method by Bayesian modeling. So, muchas gracias.
Muchas gracias, profesor Yamaguchi. Sin duda, espero que esa carretera Japón-México se haga no solo más frecuente, más ancha, que incluya más instituciones también. Para mí es un placer trabajar con ustedes, colaborar con ustedes, y espero que otros grupos aquí en México también se beneficien de sus investigaciones conjuntas. Creo que tenemos un poco de tiempo. Si tuvieran preguntas para este grupo de japoneses, antes de pedirle al doctor Nakamura que dé algunas conclusiones. Si hubiera alguna pregunta, any questions that anybody would have from the audience for them?
Hi, thank you very much for your participation here in Mexico. I would like to ask you about the predictive value of analyzing this kind of markers that you have been talking about in the embryo. When we analyze, and we are now able to analyze the complete embryo genome before the implantation for infertility solving purposes. Do you know what predictive applications are going on right now?
So in collaboration with the Kyoto IPS Center, the software pipeline I showed yesterday, Genome, is used at SILA for analyzing whole genome sequencing. The purpose is simple, very simple. Before IPS and after IPS, genomes are different. Genome structures and the copy numbers are different. And they want to select the IPS cells without heavy genomic aberrations. And this is also applicable to embryonic stem cell genome analysis. And also RNA sequencing data can be analyzed with genome I mentioned yesterday. And we have not done about something like TCR data analysis yet, but if you are interested in, all of our members are willing to collaborate with you. Yeah, that's it.
Muchas gracias, profesor Millano. ¿Alguien más tendría alguna pregunta para nuestros invitados? Es el momento, y si no, pasamos con el doctor Yusuke Nakamura para que nos dé unas palabras de conclusión. Conclusion words or remarks about this seminar. Please, Professor.
So now today's symposium is over, and with the very fruitful collaboration may start after this meeting. And I was a little bit shocked because Dr. Yamaguchi showed the bilateral collaboration. He left Chicago, but I like to say, first of all, I'd like to say thank you to the Martha for organizing this kind of meetings, and she spent lots of time. But I think the symposium is very important for the bilateral relationship between Mexico and Japan. And I think although the meeting is over, the workshop will start tomorrow, and our collaboration will expand after these 4-day meetings. And to be honest, I will come back to Japan on July 1st. I will take 2 positions. One is as a director of the Cancer Precision Medicine Center in the Japanese Foundation for Cancer Research. And also I was assigned by the Prime Minister Abe to serve as a program director for the AI, Artificial Intelligence Program, Artificial Intelligence Hospital Program. And last night, we had a hot discussion about artificial intelligence, and Dr. Millano has been working on this kind of subject for many years. So AI is very important in many aspects, particularly in medicine. So AI is very important. So AI can help the more accurate diagnosis, can help the prediction of the most appropriate drug to cancer patient and other disease area as well. And also the AI can help the maybe labor of the doctors and nurses, and the AI can fill the gap between the scientists and the doctors or medical workers, and also fill the gap between the medical workers and also patient and the family members. And I wish this can be the first step of our tight collaboration. And so I'll come back to Japan, and so bilateral collaboration is okay to me. So I think we should have this kind of opportunity very frequently, at least once a year. If you wish, come to Japan and learn something. We are quite happy. Dr. Millano and I discussed. We are quite happy to accept any student or doctors or scientists who are interested in this field. I think medicine is borderless. It doesn't matter, either a patient in Mexico, a patient in Japan. We should work together and help the patient and get their smiling back. And so our efforts are very important for 2 countries and also for international effort, as a part of the international effort. So after this meeting is over, if any of you have any kinds of questions, please ask individually to any scientist who gave a talk yesterday and today. I'm very happy to talk to the young scientists. So I believe that one of my missions is to encourage the young scientists and educate young scientists, mentor young scientists, and make the world better than now. Thank you for paying attention and thank you for your participation.
Ahora vamos a venir los dos. Brevemente, solamente un anuncio para mañana a los estudiantes del Sinvestav que van a participar en el taller. Por favor, tienen que avisar su deseo de incluirlos en el transporte del Sinvestav a Abacus explícitamente para que les puedan contestar si tienen cupo para llegar. Y sin más, le pediría al doctor Martínez Palomo.
Professor, we want to thank you for your generosity, for spending so much time with us, your precious time, your wisdom, your colleagues. Really, it is exceptional. This will continue for the rest of the week. We appreciate enormously the possibility of being in contact with you. I am sure that some collaborations will develop. We do have, as you know, some of our best students that would like to spend some time with you in Japan. We have been very selective in terms of being assured that they have the will, the interest in spending some time in your laboratories. So we really appreciate your presence. Thank you very much for being here. Yo quisiera, antes de terminar pasando a español, dar un agradecimiento muy grande a todas las personas que participaron y que hicieron posible en este simposio. En primer lugar, yo quiero que le demos un aplauso a la doctora Marta Espinosa. Porque además de sus muchas labores, dedicó un tiempo muy importante para preparar esto. Ella y junto con el profesor Nakamura son los responsables de que tengamos esta colaboración espléndida en esta semana. Yo quiero también agradecer a los miembros del Colegio Nacional, a todo el personal del Colegio Nacional por trabajar como siempre excepcionalmente, y quiero un muy caluroso aplauso para los traductores. Finalmente damos por terminada esta parte del seminario. Muchísimas gracias. Thank you very much for being here. Lunch is ready and the margaritas also. Adelante.